A rock the size of a small city just proved that everything scientists thought they understood about how the asteroid belt works might be fundamentally wrong. Not slightly off, not in need of adjustment. Wrong in a way that forces researchers to go back and rethink assumptions that have been sitting unchallenged for decades. And the most disorienting part of the whole story is this. NASA was not even trying to find it. They were running a rehearsal, a warm-up, a system test before the real mission even begins. The paper describing what they found was published in the journal Science on June 18, 2026, 2 months ago. Lead author Dr. Simone Marchi, deputy principal investigator of the Lucy mission, put it plainly. This is just one of many surprising things learned since NASA's Lucy spacecraft flew by Donaldjohanson on April 20th, 2025. That sentence is doing a lot of quiet work, because what the paper actually describes is an asteroid that wobbles on two axes simultaneously, is shaped in a way nobody predicted, and carries chemical evidence that liquid water once existed inside it. And Donaldjohanson was not even supposed to matter. It was a rehearsal target. The real destinations have not been visited yet. This is the story of the Lucy mission and what it has already found. On a pair of rocks that everybody assumed were too small, too ordinary, and too unimportant to produce anything worth stopping for, Lucy launched from Cape Canaveral on October 16, 2021. The name comes from a famous fossil, a 3.2 million-year-old partial skeleton of an ancient human ancestor discovered in Ethiopia in 1974. That fossil, named Lucy, gave scientists an unexpected window into the origins of our species. The spacecraft named after it is designed to give scientists an equally unexpected window into the origins of our solar system. The logic behind the mission is this. Trojan asteroids have been gravitationally trapped in two swarms, one leading and one trailing Jupiter in its orbit around the Sun, and are thought to be fossils from the solar system's rough and tumble early days, ancient relics pushed into their current locations by violent gravitational upheaval billions of years ago. They have been sitting in those same orbital positions, essentially unchanged, for most of the history of our solar system. Studying them is as close as planetary science can get to reading the original recipe of how planets form, and no spacecraft has ever visited one, not once, not in the entire history of space exploration. Lucy is on a 6-year trip to the vicinity of Jupiter and will arrive at the first of its primary Trojan targets in August 2027. Before it gets there, it has been making test flybys of smaller, ordinary asteroids in the main belt between Mars and Jupiter. Practice runs, system checks, the kind of engineering work that generates calibration data and not headlines. The first practice run was in November 2023 at a half-mile-wide asteroid called Dinkinesh. It was chosen because it seemed boring. Scientists spotted it as a target of opportunity because Lucy would be passing close enough to use it for instrument testing, and nobody expected to find anything remarkable. What came back from that encounter was a moon, a previously undetected satellite orbiting Dinkinesh that Earth-based observations had completely missed. And not just any moon. When the images were processed, it was clear the moon itself was two objects, two separate rocky bodies fused gently together, orbiting the main asteroid as one unit. Scientists call this configuration a contact binary satellite. It had never been observed before in the entire history of solar system exploration. The very first test flyby of the entire mission produced a discovery with no precedent in planetary science. Then came Donaldjohanson. And the second practice run was, if anything, stranger than the first. NASA's Lucy spacecraft discovered that asteroid Donaldjohanson is a wobbling, peanut-shaped relic born from a violent collision and slowly reshaped by the subtle force of sunlight. The flyby happened on April 20th, 2025, Easter Sunday. Lucy swept to within 960 kilometers of the asteroid, roughly 600 miles, at a closing speed of approximately 30,000 miles per hour. The encounter window was so brief that the spacecraft's instruments had to shut down automatically 40 seconds before closest approach to avoid pointing directly at the sun. What it collected in the time it had was enough to fill a paper in one of the most prestigious scientific journals on the planet, and produce 3 separate findings, each of which would have been considered significant on its own. Start with the shape. Before the flyby, Earth-based observations had suggested Donaldjohanson was elongated based on its brightness variations. What the Lucy images actually showed was more unusual than elongated. The flyby revealed that the asteroid resembles a peanut, with a 2-lobe structure connected by a narrower neck, 2 distinct bodies fused at a central junction, like a barbell. The larger lobe carries more craters, suggesting it has been sitting exposed to space for longer. The smaller lobe is smoother. The neck connecting them, the narrow bridge where the 2 pieces joined, is shaped in a geometry that NASA's own announcement described as 2 nested ice cream cones placed tip to tip. Preliminary analysis of the images showed the asteroid is larger than originally estimated, measuring about 5 miles long and 2 miles wide at its widest point. It is one of a family of fragments cleaved off the much larger asteroid 163 Arigoni during a collision roughly 130 to 150 million years ago. The two pieces that make up Donaldjohanson today did not shatter and scatter. They drifted apart slowly after the parent body broke up, and then, over time, drifted back together under their mutual gravity and settled into contact. Not a collision in the violent sense, more like two fragments from the same destroyed object slowly finding each other again in the dark. Then the rotation data came in, and this is where the science team stopped and started running numbers again. Earth-based telescopes had measured Donaldjohanson rotating on a roughly 10-day cycle, slow by asteroid. Standards, but perfectly measurable. And what Lucy's data revealed was that the 10-day rotation was only part of the picture. The asteroid rotates end over end once every 10.5 Earth days, while also wobbling around its horizontal axis once every 26.5 days. Two simultaneous rotational motions on two different axes. Scientists call this a non-principal axis rotation state. It means Donaldjohanson does not spin cleanly the way a ball or a top does. It tumbles through space in a pattern that repeats on both timescales at once, like a poorly thrown football that is simultaneously rotating along its long axis and wobbling around its short one. Most asteroids settle into a single stable spin over geological time as small perturbations damp out. Donaldjohanson has not. It is caught in a state of perpetual compound rotation that the existing models for asteroid spin evolution had not predicted for an object of this age and composition. A spectral analysis of the asteroid's cratered surface also revealed a similar composition to other Arigoni family asteroids, particularly the presence of iron-bearing phyllosilicates. Iron-bearing phyllosilicates is the scientific name for iron. Rich clay minerals. And clay minerals do not form from dry rock. They form when liquid water reacts chemically with rocky material over a sustained period of time. Finding them on the surface of Donaldjohanson means that at some point in the history of its parent body, before that parent body was shattered, 130 to 150 million years ago, there was liquid water present. Not ice, not vapor. Liquid water interacting with rock inside an asteroid in the main belt. The team notes these phyllosilicates indicate an aqueous evolution on the parent body, but also note that the water-induced mineral alteration was likely halted at an early stage due to insufficient water or heat. It was a brief encounter with liquid water, not a prolonged one, but it happened. And it happened in the asteroid belt. To understand why this matters, you have to ask where Earth's water came from. It is one of the biggest open questions in planetary science. Earth formed in the inner solar system where temperatures during the planet-building era were high enough to drive off volatiles. Water should not have survived the formation of Earth in meaningful quantities, and yet the planet is mostly covered in oceans. The leading explanation is delivery by impact. Asteroids and comets carrying water from the cooler outer solar system smashed into early Earth and deposited the water that eventually became the oceans. The composition of Earth's oceans closely matches predictions for certain water-bearing asteroid types. Donaldjohanson is a member of the Arigoni asteroid family, created in the inner main belt, not far from the source regions of near-Earth asteroids Bennu and Ryugu, recently visited respectively by NASA's OSIRIS-REx and JAXA's Hayabusa 2. Both Bennu and Ryugu also showed clay minerals indicating past water, but the clays on those asteroids are magnesium-rich, suggesting longer-duration water episodes inside larger, more thermally active parent bodies. The iron-rich clays on Donaldjohanson suggest a shorter, less complete episode of water chemistry. A different chapter, a different source region, a different moment in the early solar system's history. What Lucy is doing, flyby by flyby, even in these warm-up encounters, is building a comparative database of water chemistry across different asteroid families in different regions of the belt. Each one is a data point in the story of how water moved through the early solar system and how some of it ended up on Earth. Dr. Hal Levison, principal investigator of the Lucy mission, said after the Donaldjohanson flyby that the warm-up asteroids are proving to be quite interesting in their own right. That is the single most understated sentence in the history of this mission. These were supposed to be unimportant. They were test targets, chosen for orbital convenience and instrument calibration, not for scientific novelty. And both of them produced firsts in planetary science. Dinkinesh gave the first ever confirmed contact binary satellite. Donaldjohanson gave a compound rotating peanut-shaped asteroid with signs of ancient liquid water and a neck. Geometry that had no parallel in the catalog of previously visited small bodies, and the real targets have not been visited yet. Lucy will arrive at the first of its half-dozen primary Trojan targets, the asteroid Euripides, in August 2027. The Trojans are believed to be among the most primitive objects in the solar system. Dark, carbon-rich, possibly carrying organic molecules that predate the formation of Earth. Some researchers think they formed in the far outer solar system, well beyond Neptune, and were gravitationally captured into Jupiter's orbit during a period of massive planetary migration early in the solar system's history. If that is true, they are not local objects at all. They are visitors from the outer edges of the protoplanetary disk, carried inward by the gravitational reshuffling of the giant planets, and then frozen in place at Jupiter's orbital distance for 4.5 billion years. No spacecraft has ever seen one of them up close. Everything the scientific community believes about what the Trojans look like, what they are made of, and what their surfaces record about the conditions of the early solar system is built entirely from telescope data, models, inferences. Lucy has already demonstrated twice what the gap between inference and direct observation looks like. Dinkinesh was supposed to be a boring half-mile rock. It had a moon nobody had detected. That moon was made of two moons fused together. Donaldjohanson was supposed to be a simple elongated contact binary. It was tumbling on two axes, carrying ancient water chemistry, and wearing a neck shaped like no other junction ever photographed in the history of asteroid science. Whatever the Trojans actually look like when Lucy arrives in 2027, the only safe prediction is that at least some of it will be nothing like what the models predicted. That is what this mission has already shown. The universe in close-up is consistently stranger, consistently richer, and consistently more complicated than the view from a distance. Lucy is out there right now, moving through the main asteroid belt at 30,000 miles per hour, heading for Jupiter's orbital neighborhood. The team at Southwest Research Institute, NASA Goddard, and Johns Hopkins APL is tracking it every day. The data from Donaldjohanson was published 2 months ago. The next data comes in 2027. Tom Statler, program scientist for the Lucy mission at NASA headquarters, said after the Donaldjohanson flyby, "These early images are again showing the tremendous capabilities of the Lucy spacecraft as an engine of discovery. The potential to really open a new window into the history of our solar system when Lucy gets to the Trojan asteroids is immense." That word, immense, is doing real work. Because Lucy has already found something that had never been seen before in the history of solar system exploration on each of its first 2 test encounters. 2 warm-up stops, 2 firsts in planetary science, 2 objects that were supposed to be unremarkable and turned out to be nothing of the sort. The Trojans have been sitting in the dark at Jupiter's orbital distance, untouched and unvisited, for 4.5 billion years. Whatever they look like when the cameras arrive, whatever chemistry they carry, whatever structures they show that no telescope from Earth has ever resolved, it will be the first time any human instrument has ever seen it. And based on what Lucy has already found on the rocks that were not even supposed to matter, the expectation that the Trojans will be straightforward seems like the one assumption nobody in this field is still making.